The Doppler effect is the change in frequency of a wave due to the relative motion between the source and the observer. So consider the source as a truck, for example, sounding its horn continuously, and the source is moving at a velocity vs. So at time t equals 0, a sound wave starts to propagate out at a velocity v. Now at a time equal to the period of the wave, this wavefront has propagated a distance of lambda s, and the source has displaced a distance of delta xs. And at this time, another sound wave starts to propagate from the source. So the distance between the wavefronts, which is the wavelength heard by the observer, is lambda O, and treating the source as a particle, we measure the distance between the wavefronts from the center of mass of the particle. So the wavelength heard by the observer is equal to lambda s minus delta xs. And using the relationship between the wavelength and the frequency, we have lambda O is the speed of sound on the frequency heard by the observer, and lambda s is the speed of sound on the frequency of the source. And the displacement of the source over one period is equal to the speed of the source multiplied by the period of the source, where the period is the reciprocal of the frequency. So we can divide this by fs. So this is equal to the speed of sound minus the speed of the source on the frequency of the source. Now if we take the reciprocal of both sides, we have FO on V is Fs on V minus Vs. And multiplying through by the speed of sound, we get the frequency heard by the observer as the speed of sound on the speed of sound minus the speed of the source by the frequency of the source. So in this case, the source is moving towards the observer, and the observer is stationary. So in this case, the observer is going to hear a higher frequency than that of the source. Now if the observer was instead over here, then you're going to get lambda s being this distance, and lambda O is going to be this distance, which is the distance between the two wavefronts. So you get the wavelength heard by the observer is equal to the wavelength of the source plus the displacement of the source. So that'll give you a relationship being the frequency heard by the observer is equal to the speed of sound over the speed of sound plus the speed of the source by the frequency of the source. So in this case, the source is moving away from a stationary observer, and therefore the observer will hear a lower frequency. So in general, we have the frequency heard by the observer is V on V plus or minus Vs by the frequency of the source. Now in the case where you have the source being stationary and the observer is moving towards the source, then you'll get a similar expression with the frequency heard by the observer. We'll have the speed of sound plus the speed of the observer, being VO, over the speed of sound by the frequency of the source. So when the observer moves towards the source, then the frequency that's heard by the observer is higher. And if the observer is moving away from a stationary source, then the frequency heard by the observer would be lower. So combining these two equations, we have FO is equal to the speed of sound plus or minus the speed of the observer over the speed of sound plus or minus the speed of the source by the frequency of the source. So in this case, for example, if you have the source moving away from the observer and the observer moving towards the source, then given the source is moving away from the observer, that's going to cause a drop in frequency. So you take the positive sign in the denominator. And given the observer is moving towards the source, then you have a plus over here, as you'd have an increase in frequency. And if the velocities of the source and observer are the same, there's no relative motion between the source and the observer, so therefore the frequency heard by the observer will be the same as the source frequency. A truck sounds its horn at 100 Hz as it moves at a speed of 72 km an hour. Now assuming the speed of sound is 340 meters per second, which is a typical speed in air at 20 degrees, determine the frequency heard by a stationary observer as the truck approaches the observer. So that's part A. So we have our observer being stationary and our source approaching the observer at 72 km an hour. So recall that our equation for the Doppler effect is the frequency heard by the observer being equal to the speed of sound plus or minus the speed of the observer on the speed of sound, or the wave speed, plus or minus the speed of the source by the frequency of the source. So in our case, the observer is stationary, so this is 0. So our equation can be written as follows. Now given that the speed of the source is 72 km an hour and the speed of sound is given in meters per second, then we need to convert one or the other into their consistent units. So let's convert the speed of the source into meters per second. So we have 1000 meters per kilometer and 3600 seconds per hour. So the speed of the source is 20 meters per second. So given that the source is approaching the observer, then we expect the frequency heard by the observer to be higher than that of the source. So what we get is FO is the speed of sound on the speed of sound minus the speed of the source, which is 320 meters per second, multiplied by the frequency of the source, which is 100 Hz. So that gives a frequency of around 106 Hz. And in part B, we're asked for the frequency heard by the observer as the truck passes the observer. So when the truck passes the observer, it's going in the opposite direction. So when it's moving away from the observer, we expect the frequency heard by the observer to decrease. So therefore we use the positive sign here. And therefore the frequency heard by the observer is the speed of sound in meters per second over the speed of sound plus the speed of the source. So that will be 340 plus 20 is 360 meters per second. And that's multiplied by the frequency of the source. So that gives a frequency of around 94 Hz.